So hello everyone, welcome to the channel. So in this video I'm going to show you how to calculate the urban thermal field variance index using Landsat 8 imagery in Google Earth Engine. So now let's get started. So the urbanization leads to a drastic land surface changes, particularly the replacement of natural vegetation with the impervious surfaces like concrete, asphalt, building, and these modifications significantly alters the surface energy balance and causing the urban heat island where the cities are much warmer than the surrounding rural areas. So the urban heat island effect negatively impacts the human health, energy consumption, biodiversity, and overall urban sustainability. The remote sensing and GIS, particularly, we're going to use the Landsat 8 imagery using Earth Engine to provide an efficient way to monitor and quantify the thermal environment at cities and regional scales. So, among various thermal indicators, the Urban Thermal Field Variance Index has gained an attention for linking the land surface temperature variation with ecological condition and thermal stresses in city. So, the field variance index is particularly powerful because it normalizes the land surface temperature against the mean temperature of the study region. Unlike the traditional LST or the urban heat island indices, the UTFVI provides a relative measure of how hot or the cold each pixel is in the relation to the city's overall average, making it suitable for identifying the local hotspots, the thermal comfort zones, and ecological vulnerability areas. So, by integrating the NDVI and emissivity correction and thermal infrared band processing, the analysis performs a full thermal environmental analysis over the Kuwait City for 2022. So, it first estimates the vegetation fraction and emissivity and corrects the LST, and finally derives both urban heat island and as well as the urban thermal field variance index, and offering an insight into the spatial pattern of the heat stress. So to calculate our urban thermal field variance index, first we're going to define our region of interest. So for example, we're going to specifically select this particular area as our region of interest, that is Kuwait City. So we're going to select a study area over this part of this Kuwait City here. So let me turn to a satellite mode here. So in satellite mode, you can able to visualize the city here. So this is our Kuwait city here. So you can able to see the build-up areas here. So for example, let me zoom in here. And now here you can able to clearly visualize the build-up, that is the city here. The settlements you can clearly able to observe from the satellite image. So we're going to specifically select out this particular study region here. So to do that, so first we're going to navigate to this option called draw a rectangle. So we're going to click this option called draw a rectangle. So once you click that, we have this set of options that is available here. So next I'm going to draw a study area over this particular city called Kuwait City. So let me draw a rectangle over the study region here. So once you drawn your the polygon over this over your suitable study region of your choice here, so next step I'm going to exceed this and I'm going to turn this off. And in the top section we have this new variable called geometry is pop up here, a polygon with 4 vertices, which indicates our study region. So now I'm going to copy this latitude and longitude of the study area using the option called show generated code. And from here I'm going to copy the latitude and longitude of our newly created study region using Ctrl C in my keyboard. So once you copied it, next I'm going to paste this latitude and longitude inside the variable called study area. So I'm going to select this and I'm going to paste it using Ctrl B in my keyboard. So once you pasted your latitude and longitude inside this variable called study area, so next we're going to convert this particular set of latitude and longitude into a polygon. So to do that, we're going to mention earthengine.geometry.polygon with the latitude and longitude of the study area. This, for example, this particular polygon, it is given here. So it's going to convert this latitude and longitude into a polygon. So the next step, we're going to add this layer. So to add this layer, we're going to mention map.addLayer study area with the default visualization parameter, and we're going to output as Kuwait City. And last, to center this particular object, we're going to mention map.centerObjects study area with a suitable zoom level. So let me run this code here. So now here you can able to visualize our this is our region of interest, that is our study area. So you can able to see this is our study area, Kuwait City. So in the next step, we're going to set some temporal parameter for our analysis. So our analysis period is going to start from summer to early winter. So starting from May to December. So to set our temporal parameters for our analysis, so we're going to mention a variable called analysis start is equals to. We're going to mention the start time period of our analysis, that is 2022 May 1, and similarly the end period of our analysis I'm going to mention this 2022 December 31st. So once you set your temporal parameters, next step we have to apply the scaling factors and the offset value before proceeding towards our analysis. So in our Landsat 8 imagery, let me show you that. So each satellite imagery has its own set of scaling and offset factors. For example, so this particular, that is Landsat 8 imagery, the dataset availability is from 2013 to 2025 and the dataset provider is USGS. And using this code you can access the Landsat 8 imagery. So in the band section here, so you can able to see the resolution of the band is around 30 meters, and you can able to see here starting from SRB1 to SRB7, these are the surface reflectance band. So it has a scaling factor of 2.75 into 10 power minus 5 is the scaling factor, and similarly it has an offset factor of minus 0.2. So we have to apply both the scaling and offset factor before proceeding towards our analysis. So starting from SRB1 to SRB7, these are surface reflectance band. So each band represented a given description here. Starting with the B1 represents ultra blue, and B2 that is blue, green, red, near infrared, shortwave infrared, and shortwave infrared 2. And likewise we have a ST band, that is surface temperature band here, that is the thermal band. So it has a unique set of scaling and offset factors. So you can able to see this is the scaling factor of for ST band, and this is the offset factor of our ST band, and the units and the wavelength. So wavelength of ST band of Landsat 8 imagery, it is from 10.6 micrometers to 11.19 micrometers. So the band 10 represents the surface temperature. So now let me get back to Earth Engine. So to apply the scaling factor, so first we're going to define a new function called apply image scaling. So we're going to create a function called apply image scaling, representing the image here, that is Landsat 8 image. And the next step, we're going to apply the scaling factor for our optical bands, that is the surface reflectance bands. That is our optical bands. So we have optical bands as well as the thermal bands. So first we're going to apply the scaling factor to our optical bands. So using a variable called optical scaled is equals to image dot select SRB dot. So it's going to select all the surface reflectance band, and we're going to apply the scaling and offset using dot multiply 0.000275, and we're going to add minus 0.2 using dot add function minus 0.2. So in the next step, we're going to apply the scaling and offset factor to our thermal bands, that is ST band, surface temperature band. So to apply the scaling and offset factor to the thermal bands, we're going to define a variable called thermal scaled is equals to image dot select ST band dot multiply the scaling factor of thermal band is 0.00341802. So which is given here. So you can able to see here, this is a scaling factor and this is the offset factor, and we're going to add the offset factor here, dot add 149 is the offset factor. And next step, we're going to replace the original band, the scaled band, that is our optically scaled band and thermally scaled band. So to do that, we're going to mention return image dot add bands optical scaled, referring to this particular variable here, that is our optical bands, and null true. And similarly to add our thermal bands, we're going to mention a dot add bands thermal scale, referring to this particular variable where we apply the scaling and offset factor to our ST band, that is surface temperature band. So that is mentioned as thermal scaled. And once we apply the scaling and offset factor to our Landsat 8 bands here, the next step we're going to apply another function to mask cloud and cloud shadows using a QA pixel band. So let me show you this particular band here, the QA pixel band. So this is the QA pixel band. So this is the pixel quality attribute generated from CF mask algorithm. So using this function, So we're going to remove the images with cloud contamination and cloud shadows. So for that we are applying this particular function called function apply cloud mask. So to apply the mask cloud and to mask out the clouds and cloud shadow, first we're going to define this function called apply cloud mask and representing my image collection here. That is our Landsat 8 imagery. So in the next step, we're going to define the bit mask for the cloud shadow. That is represented as bit 3, and for the cloud, we're going to represent it as bit 5. So first, we're going to define a variable called cloud shadow mask bit is equals to 1 is that is 3 is greater than 1, and similarly, in the next step, we're going to define another variable called cloud mask bit. So this is we're going to mask out the cloud. So for that we are defining this variable called cloud mask bit. And similarly, previous variable cloud shadow mask is used. We define this variable in order to mask out the cloud shadows. So now we define a variable called cloud mask bit is equals to, so the 5 is greater than 1 here, far greater than 1. And next step, we're going to select the quality assessment band, that is our QA pixel band. So which is I've shown you earlier. So there is QA pixel band here. So the pixel quality attributes generated from CF mask algorithm. So this is the band we're going to use it for. So for that we're going to mention a variable called quality assessment is equals to image collection, referring to this particular function, and dot select QA pixel. So we are selecting this particular band here, that is QA pixel band. And the next step, we're going to create another variable, so to mask out both the cloud and cloud shadow. So to do that, we're going to mention a variable called clear sky mask is equals to the quality assessment dot bitwise and we're going to mention cloud shadow mask bit is equals to 0. So we're going to mask out the cloud shadow by mentioning dot is equals to 0, and similarly dot and the quality assessment dot bitwise and, so the cloud mask bit is equals to 0. Similarly, the cloud it's going to be the clouds in our image, it's going to be 0 by mentioning dot equals to 0. And the next step, to apply this mask to our image, we're going to mention return image collection dot update mask clear sky mask, representing this particular variable clear sky mask. And in the next step, we're going to load our Landsat 8 imagery to perform and calculate the urban thermal field variance index analysis. So now we can proceed towards our analysis once we apply the scaling and offset factor and applying the QA pixel band in order to filter out the cloud and cloud shadow mask. And to load our Landsat 8 imagery, we're going to mention variable Landsat collection is equals to earth engine dot image collection and Landsat LC8 collection to tire L2. So this code, using this code, we can access our Landsat 8 imagery. And next step, we're going to filter it based on the temporal time period of our analysis, the start period of our analysis, and the end period of our analysis. So for that, we're going to mention dot filter date function, analysis start and analysis end. So previously, we have mentioned the analysis start period and analysis end. So let me show you that here. So this is the analysis start and analysis end period. So in the next step, we're going to filter bound based on our region of interest. So for that, we're going to mention dot filter bound study area. And next step, we're going to apply the scaling and offset factor and the cloud mask function. So we're going to apply both the function in the Landsat 8 imagery, that is dot map apply image scaling. So this particular function, which representing this particular function we mentioned earlier for applying scaling and offset factor to our optical and thermal bands. And similarly, we're going to apply another function that is dot map apply cloud mask, which representing this particular function here. We are applying this particular function to mask the clouds and cloud shadow in the image. So for that, we're going to mention dot map apply cloud mask. So the next step, we're going to create a median composite in order to reduce and fill those gaps. That is in the image we have those gaps. Once we apply this the shadow and cloud masking, there used to be a bands that is gaps in the images. So to fill those and reduce the noise in our image, we're going to apply a median composite to our Landsat 8 imagery. So to do that, we're going to mention a variable called composite image is equals to Landsat collection, referring to this particular variable, dot median function. So it's going to give us the create a median composite image to reduce the noise and fill the gaps. And the next step, we're going to define the visualization parameter for our Landsat 8 imagery. So to define our visualization parameter, so we're going to mention a variable called true color visualization, the bands. So we're going to use this set of 3 bands here for true color image. For example, we're going to use band 4. That is, let me show you that the band 4, band 3 and band 2, which represents a true color composite image. So we're going to use this set of image in this combination. So starting, we're going to mention the variable true color visualization is equals to band SRB4, SRB3 and SRB2. So in this combination, it's going to give us a true color composite image. And also we're going to set the minimum and maximum value for the image here. So for example, the minimum and maximum we're going to set to be around 0.0 and the maximum value we're going to set around 0.3. And also the Landsat 8 imagery has a minimum and maximum values already given here. From this image here, I can able to see the minimum and maximum value. So the minimum value ranges from 1 to 65,455 is the max value. So you can arrange those value according to your choice. So for example, I mentioned in this set of values here. So to add this layer, next step we're going to mention map.add layer and composite image, referring to this particular variable. So where we apply the median function and the visualization parameter, that is true color visualization, representing this particular variable, and output the layer name as true color RGB 432. So now let us visualize this particular imagery. I'm going to run this code here and let us take a look at this image here. So let me navigate to the layer section. I'm going to turn on the true color RGB 432. So it's going to load the image, and let me turn off this study area. So currently we're visualizing the Landsat 8 imagery. You can able to see here. So this is our Landsat 8 imagery, and this is our study region here. So you can able to see this hand here. So that is the mouse cursor here. So this is our study region. So I'm going to navigate to the layer. I'm going to click this option here. And the custom section, I'm going to click this option called stretch 90%. So once you applied it, next step, I'm going to click apply. So it's going to load image here. So here I can able to visualize our study region here. This is our region of interest. So you can able to clearly visualize from our image here. So let me close this. So this is our true color composite image of Landsat 8 imagery. So the next step, we're going to calculate a set of indices here. So in order to calculate our urban thermal field variance index using our Landsat imagery. So starting with, we have to calculate the normalized difference vegetation index, and followed by we have to calculate the urban heat island index, and we have to calculate the LST. So these parameters are required to calculate this particular indices, that is urban thermal field variance index. So the formula for this particular index is UTFVI, that is urban thermal field variance index, is equals to LST minus of LST mean divided by LST. So the LST, which represents the pixel land surface temperature, and the LST mean, which represents the mean LST of the study area. And the UTFVI values are dimensionless and represents how much hotter or cooler a pixel is relative to the average. So when a first step to calculate the normalized difference vegetation index. So the formula for NDVI is for Landsat 8 imagery. We mentioned NIR minus of red divided by NIR plus red. So the NIR band here, which represents the band 5, that is SR B5, and the red band, which represents the band 4, which is SR B4. So now to compute our normalized difference vegetation index, first we're going to define a variable called vegetation index is equals to the composite image. So the composite image, which refers to this particular variable, so where we apply the median function in order to reduce the noise and fill gaps, we're going to use that image, and in that we're going to mention dot normalized difference. So there is SR B5 and SR B4. So which represents SRB5 minus of SRB4 divided by SRB5 plus SRB4. And we're going to rename as NDVI, that is Normalized Difference Vegetation Index. And in the next step, we're going to add a layer. So to add layer, we're going to mention map.addLayer, Vegetation Index, representing this particular variable. And we're going to set the minimum of -1 to the maximum of +1. And the color palettes we're going to mention is blue, white, and green. So these are the following set of color palettes that are starting with blue, white, and green. And we're going to output the layer name as Vegetation Index NDVI. So now let us take a look at the NDVI here. So we're going to navigate to this option called layers, and I'm going to turn on Vegetation Index here. And I'm going to turn off this true color. So now here you can able to visualize it. Let me apply some, I'm going to navigate to the layer section. I'm going to click this option here. And the custom section, I'm going to apply stretch 90%. And I'm going to click apply here. So the value ranges from -0.8 to +0.7. So you can able to see from this image here comparatively. So this study region has a vegetation comparatively very less here. So for example, only few portion in the study area which indicates the presence of vegetation here. For example, this particular area. So this particular area clearly indicated that it has a vegetation. Let me turn to a satellite mode. So which is clearly which indicates here you can able to see this. So some agricultural activity is being taking place here. So you can able to see from this base image here. So you can able to see that. And other areas is completely, it is a barren area here. So you can able to see from this image. Let me turn to vegetation index, that is normalized difference. So even in the cities, city in this study region has only few vegetation areas in this area. So you can able to see that temperature. So all the green color which indicates the vegetation, and the whitish color which represents the non-vegetation areas. So let me close this. So in the next step, we're going to calculate the statistics for the NDVI to establish a range for vegetation fractions. So for example, we're going to calculate the minimum vegetation index, the maximum vegetation index, and last we're going to calculate to calculate our final index, that is urban thermal field variance index analysis. So to calculate the minimum NDVI and the maximum NDVI value, so first we're going to define our variable called the variable minimum vegetation index is equals to earth engine dot number vegetation index referring to this particular variable, and we're going to apply some statistical function dot reduce region. So the reducer, I'm going to mention earth engine dot reducer dot minimum, which is going to give us a minimum NDVI value, and the study area is geometry, and the spatial resolution is 30, the max pixel value, and last to get the first value out of it, we're going to mention dot get 0. So this is very useful for minimum and maximum in order to find out the vegetation fraction. So for that we are calculating the minimum and maximum NDVI values. So the next step, we're going to define another variable called max vegetation index to calculate the maximum NDVI value. So we're going to mention earth engine dot number vegetation index dot reduce region. Reducer, I'm going to mention earth engine dot reducer dot max, the max function here to compute the NDVI max value, and the geometry is study area, spatial resolution is 30, the max pixel value, and to get the first value out of the result, we're going to mention dot get 0. And last step, we're going to calculate the fraction of vegetation, that is FV. So FV, which represents the fraction of vegetation. So to calculate that, we require a minimum and the maximum NDVI value. So to calculate the fraction of vegetation, we're going to mention a variable called vegetation fraction is equals to vegetation index subtract minimum vegetation index dot divide maximum vegetation index subtracting minimum vegetation index to the power of 2, that is dot power earth engine dot number 2, and last we're going to rename as FV, that is fraction of vegetation. So in the next step, we're going to calculate the emissivity based on the vegetation fraction. So the more vegetation is equals to the higher emissivity. So now to calculate the emissivity value, first we're going to define a variable called surface emissivity is equals to vegetation fraction so which refers to this particular variable of vegetation fraction, so which we calculated using the minimum and maximum NDVI values. And the next step to find out our surface emissivity, so we're going to use the vegetation fraction and we're going to multiply with the number 0.004 and add by the number 0.986, and last we're going to rename as EM, that is surface emissivity. So for that we use this variable called surface emissivity is equals to vegetation fraction dot multiply earth engine dot number 0.004 dot add earth engine dot number 0.986, and last we're going to rename as EM, that is surface emissivity. And this particular factor is very essential in order to calculate the urban thermal field variance index analysis. For example, let me show you this particular formula. So we have to calculate this particular one here, that is our urban thermal field variance index. So this is the formula: UTFVI is equals to LST minus LST mean divided by LST. So next we have to calculate the LST. So LST, which requires this set of parameters, for example BT divided by 1 plus lambda multiplying BT divided by rho multiplying so we have the natural log multiplying the surface emissivity and subtracting by 273.15. So we require to calculate this emissivity value now. So using this formula we can calculate the emissivity value, that is vegetation fraction multiplying the number 0.004 and we're going to add by the number 0.986, and last we're going to rename as EM. So in the next step we're going to select the thermal band for the temperature calculation. So to do that we're going to define a variable called thermal band is equals to the composite image dot select ST beaten, that is surface temperature band in Landsat 8 image, and we're going to rename as thermal. So this particular band, ST band, will be going to renamed as a thermal band. And the next step we're going to calculate the land surface temperature using the emissivity correction, and this is the formula to calculate the land surface temperature. So this is derived from the Landsat 8 imagery. So we have to apply this formula, that is BT LST is equals to BT divided by 1 plus lambda multiplying BT divided by rho and multiplying the natural logarithm of emissivity value subtracting 273.15. So here the BT represents the brightness temperature in Kelvin, and the lambda, which represents the wavelength of emitted radiance, which is 11.5 microns for Landsat 8 image, and the rho, which represents the H multiplying C divided by sigma, so which has an approximately the value of around 14,318 micrometers per Kelvin. And the last is the emissivity, that is represented in this symbol. The surface emissivity is derived from the vegetation fraction. The high vegetation indicates high emissivity value closer to 0.99. So to apply this formula here, so there is LST is equal to BT divided by 1 plus lambda multiplying BT divided by rho multiplying natural log of emissivity value and minus subtracting by 273.15. So to do that, we can apply this particular formula. We're going to define a variable. Land surface temperature is equals to the thermal band. So referring to this particular variable where we selected the ST band and we renamed as a thermal. And here I'm going to mention this dot expression, the brightness temperature divided, here we applying the formula, the brightness temperature BT 1 plus 11.5 multiplying the brightness temperature divided by the 14,318 and multiplying the log emissivity value subtracting 273.15. So here the brightness temperature, which represents the thermal band, so we are representing this variable called thermal dot select thermal, so its units in Kelvin. And similarly the surface emissivity, the emissivity is represented as the surface emissivity variable, so which represents this particular variable, and it is unitless. And last we're going to rename as LST. And next it is the visualization parameter for our LST. So to define a visualization parameter, we're going to mention a variable called temperature palette is equals to, and these are a set of colors which going to represents the LST value, LST colors here. And next is we're going to define another variable called temperature visualization. This is for the visualization purpose of this of the land surface temperature. So we set a minimum of 7 and to a maximum of 50. So the value ranges from 7 to 50 degrees Celsius, and the palettes we're going to mention is temperature palettes, which represents this particular variable. And last, to add this LST layer to the map, we're going to mention map.add layer, LST land surface temperature, representing this particular variable, where we apply the formula, and temperature visualization, which represents this particular variable, where we apply the visualization parameter, and output the layer name as land surface temperature. And to center this, we're going to mention map.center object study area 9 and the suitable zoom level of 9. So let me run this code here and let us visualize the result. So this is the land surface temperature here. So let me navigate to this option, and I'm going to select to stretch 90%. So you can able to see the value ranges from 26.86 degrees Celsius to 54.44 degrees Celsius, and I'm going to click apply, and now let us visualize the result here. So you can able to clearly distinguish this particular portion of this area. So all this yellow color, which indicates the urbanized area in Kuwait City, here you can able to see that compared to this compared to the city, the surrounding areas has a very high temperature. Based on the color code here, you can able to observe the compared to the city, the other surrounding of the study region has a very high temperature here based on the color tone here. And also we can use our inspector tool to analyze this particular one. So let me use my inspector tool. So I'm going to navigate to the inspector tool here, and I'm going to click this option here. So I'm going to place my inspector tool over the study, over the build-up areas in Kuwait City. So you can able to see that land surface temperature for the over the study area is around 43.80 degrees Celsius. Let me place it somewhere else here, and now it is currently around 47. So you can able to see it is around 47.32 degrees Celsius. So let me place the value outside the city areas. So you can able to see the value is around 52.29 degrees Celsius. And let me place my cursor over this area closer to the city. So now the value is around 50.11 degrees Celsius here. So you can able to observe the distinct. So you can able to observe this distinct variation here between the city areas versus surrounding areas. The surrounding areas has a very high temperature. For example, towards towards the eastern section of the study area. So I'm gonna place my inspector tool over there. So which is around 52.6 degrees Celsius of temperature, which is observed here. So let me turn off this layer and turn to a satellite mode here. Let me zoom in here, and you can able to see these areas are completely of so it is more of industrial areas here, and the temperature is comparatively is pretty high here, pretty high in these regions here. So you can able to see there is a very high temperature areas. Let me place my inspector tool over the study area, so which is around 56.25 degrees Celsius of temperature. So once we found the LST, next step we're going to calculate the urban heat island. So let me show you the formula. So to calculate our so in the next step we're going to calculate the urban heat island index using z-score normalization. So the urban heat island index measures how much each pixel deviates from the regional mean land surface temperature. So urban heat island is equals to LST minus of LST mean divided by the standard deviation of LST. So where the LST is equals to the pixel land surface temperature, and the LST mean is equals to the mean temperature of study area, and last LST represents the standard deviation of LST. So using this formula, we're going to compute our urban heat island index. So first we're going to define a variable called mean surface temperature is equals to earth engine dot number land surface temperature dot reduced region, and here we're going to apply the statistical function called reducer earth engine dot reducer dot mean function. So to calculate the mean surface temperature, mean land surface temperature, we are applying the statistical function called dot mean function. So the geometry, we're going to mention the study area, and the spatial resolution is 30 meters, and the max pixel values we're going to mention is 1:10⁹. And last, to get the values, get the mean land surface temperature out of the first value. So we're going to mention dot get 0 to get the first value out of it. And similarly, we're going to define another variable called standard deviation, that is standard land surface standard deviation, the land surface temperature. So to calculate that, we're going to mention a variable std surface temperature is equals to earth engine dot number land surface temperature dot radius region, and the radius are going to mention earth engine dot radius dot standard deviation, and the geometry you're going to mention as study area, and last is spatial resolution is 30 meters, and the max pixel value is 1 to 10 power 9, and to get the first value out of it, we're going to mention dot value function and dot get 0. And last, to visualize the temperature statistics in console, for example, to see the mean land surface temperature in the study area in degrees Celsius, we're going to mention a sprint mean land surface temperature in the study area in degrees Celsius, and we're going to refer this particular variable called the mean surface temperature. And similarly, to visualize the standard deviation of the land surface temperature in the study area in degrees Celsius, we're going to mention print standard deviation of the land surface temperature in the study area in degrees Celsius as a std surface temperature. So now let us take a look at this value here. I'm going to run this code. So in the console section, I can able to see the mean land surface temperature of the study region, which is around 46.2195 degrees Celsius, and the standard deviation of the land surface temperature is around 8.61 degrees Celsius. So now we have both the mean land surface temperature variable as well as the standard deviation of land surface temperature. From the formula, what is required is 3 variables. One is LST, and next is the LST mean, and next is the standard deviation LST. So now we have 3 variables to compute the urban heat island index. So now to compute the urban heat island index, we're going to mention the variable urban heat island index is equals to the land surface temperature. So now we are applying the formula, that is dot subtract means land surface temperature, and dot divided by standard deviation of land surface temperature, and last we're going to rename as UHI, that is urban heat island. And next we're going to set the visualization parameter for the urban heat island. So we're going to mention the variable urban heat island is visualization is equals to the mean, we're going to mention the value is -4, and the minimum value we're going to mention is -4, and the maximum value we're going to mention is +4. So the value which represents the standard deviation below the mean. So here the value was standard deviation below mean and the standard deviation above mean. So now we set the value according to standard deviation, the minimum of -8 to maximum of +8. So it's a standard deviation below mean and standard deviation above mean. So these are the following set of color palettes here to visualize our urban heat island index. And last is to add the layer, we're going to mention map.add layer urban heat island index referring to this particular variable, and visualization for visualization referring to this particular variable. And last, we're going to output the layer name as urban heat island index. So now let us take a look at the urban heat island index. We're going to run this code. Let me navigate to the layer section. I'm going to turn off all of the layers. So now we are currently visualizing the urban heat island index here. So we're going to navigate to the setting option here. I'm going to click the custom section and make sure that I'm going to select stretch 90%. So once you selected that particular value, I'm going to click apply. So here you can able to visualize the color here. So only in this cities areas has a lesser temperature compared to the surrounding area. Most of the temperature is very high compared to the based on our inspector tool here. So you can able to see the value here. So which has a value of around 45 degrees Celsius. I'm going to place the value over the outside the city. So let us visualize the value, which is around 51.68 degrees Celsius of temperature. And this is you can able this is a layer of urban heat island index, and the value which ranges from this set of values here, that is -1.8 to +1.0. And last we have to calculate our urban thermal field variance index. So to calculate the urban thermal field variance index, we are going to apply this particular formula. So to calculate the urban thermal field variance index, so this particular index is designed to classify the ecological evaluation based on the heat stress. So its formula is UTFVI is equals to, so to calculate the UTFVI, we require only LST and LST mean value. So this is the formula. So again, LST which represents the pixel land surface temperature, and LST mean which represents the mean LST of the study area. So the UTFVI values are dimensionless and represents how much hotter or the cooler a pixel is related to the average. So now to compute our urban thermal field variance index, first we're going to mention the variable called UTFVI index is equal to the land surface temperature. So we're going to apply the formula, that is land surface temperature dot subtract function mean surface temperature dot divide land surface temperature, and last we're going to rename as UTFVI, that is urban thermal field variance index. So now to set the visualization parameter for the UTFVI index, we're going to mention the visualization parameter using the variable UTFVI visualization. We're going to set the minimum of -1 to the maximum of 0.3, and the color palettes, we're going to mention this set of value here. So these are the following set of color palettes for indicating the high and indicating the low and high values. And last, to add this layer, we're going to mention map.add layer UTFVI index UTFVI visualization, and we're going to output as urban thermal field variance index. So now let me navigate to the layer section here, and I'm going to turn on this particular this layer called urban thermal field variance index, and let us take a look at this particular variable. And this particular layer, there is our raster image of urban thermal field variance index. And from here I'm going to navigate to the layer, and I'm going to click this option, and I'm going to select the stretch type to stretch 90%. So once you selected the value here, so we have the value ranging from -1.067 to 0.091. so this is the value ranging from -1.06 to plus 0.091, and I'm going to click apply. So you can able to see high values are represented in this set of color, and the low values are represented in this set of colors here. So let us, before proceeding towards our visualizing this layer, let us check out this values. So the UTFVI interpretation values here. So starting with the UTFVI value, so next is we have the ecological evaluation here, and followed by the environmental conditions. So starting with the UTFVI value here, if it's lesser than 0.005, it is excellent, no heat stress, and if the value ranging from 0.005 to 0.015, it is good, the weak heat stress. And last is the next is a value ranging from 0.015 to 0.025. It is ecological evaluation is normal, and it is of moderate heat stress. And the next is a 0. The value ranging from 0.025 to 0.035. The ecological evaluation is bad, and it is a strong heat stress. And if the UTFVI value is greater than 0.035, it is worst. Based on the ecological evaluation, it is very strong heat stress. So based on this value, let us check out these values we are visualizing it currently. So we have the three distinct set of colors here, starting with the red, orange, so and a few dots of yellows that is available. So based on the inspector tool here, I'm going to use my inspector tool. I'm going to select over this city area. So this is the Kuwait City. So we're going to place my inspector tool over this area, and let us take a see the values here. So the values of it is around UTFVI value is around 0.03. So let us take a look at the interpretation value. So which is 0.03. Let me check one more time here, which is 0.032. So 0.032. So which is falling within this value, which is bad. So strong heat stress, which indicates a strong heat stress. So which in the study areas, the city which faces a strong heat stress in Kuwait City. And similarly, let me place my inspector tool over this set of areas here. So now we can able to see the values. So the value which is false, the values, so the outside the city, the value is around 0.1 to 0.10. So 102. So let us check those values here, 0.102. So you can able to see that the value falls greater than 0.035. So in this situation, it is the worst ecological evaluation and very strong heat stress areas. And last, let us take a look at the agricultural areas. So somewhat the color is around it is of yellow in color, and I'm going to place my inspector tool over those area. So you can able to see place my inspector tool, and you can able to see the values from here. So which is around minus 0.219. So minus 0.219, comparatively the negative value, which indicates it is of excellent area and no heat stress is observed on those areas, and the ecological values states it is excellent. So the agricultural area in Kuwait City is comparatively no heat stress zone, and compared to other parts of very strong heat stress and strong heat stress is the classification. So now let us take a look at the cities with the highest recorded temperature. So these are the cities located in the hot desert climates, often holding the world's record temperature. Starting with a city called Death Valley. So the country is in USA, the North America. The highest recorded temperature, which is around 56 degrees Celsius. So it is officially the hottest place on the earth, a desert basin below the sea level. And followed by the Kuwait. Kuwait is located in the Middle East, and the recorded temperature is around highest recorded temperature. It is around 54.54 degrees Celsius. So regularly it experiences a temperature above 50 degrees Celsius in summer. And next is Iran, which are located in Middle East. So the highest recorded temperature, which is around 54 degrees Celsius, one of the most consistently hot cities on earth in the summer. And next is the Phoenix, Arizona. So USA, North America. So the highest recorded temperature, which is around 50 degrees Celsius. So the largest American city with such extreme heat faces major urban heat challenges. And next is Israel. It's located in the Middle East, around 54 degrees Celsius, holds a record for Asia. And next is the Pakistan, located in South Asia, which is the highest recorded temperature is 52 degrees Celsius. So not only extremely hot but also humid, making it dangerously uninhabitable. So now let us take a look at the application part of this analysis. So urban thermal field variance index has a wide range of applications in urban and environmental studies. So starting with the first application, which states the urban climate studies. So it identifies and localizes the heat island within cities and assesses the spatial variability of the urban heat stress. So the second is urban planning and policy making. So it guides the placement of green infrastructure, parks and cooling corridors, helps design the climate resilient cities. And the third application is the human's health and comfort. So evaluates the areas of potential thermal discomfort and heat related health risk and supports the heat wave risk assessment. And the fourth application is the ecological monitoring. So it detects a degradation in urban ecosystem caused by an excessive heat, monitors the vegetation stress in densely built up regions. And the fifth application is sustainable development goals. So it contributes to SDG 11 and SDG 13 by supporting the heat mitigation strategies. And last is the comparative studies. So UTFVI enables the intercity or intracity comparison across time and space, useful for the long-term monitoring of climate change impact in urban areas. So in this video I have shown you how to calculate the urban thermal field variance index using Landsat 8 imagery in Google Earth Engine. And thanks for watching, and make sure that you subscribe to our channel and give us a like.